So
Sure.
I'll finish in 30 seconds.
Oh, okay. Or if you are just going to read it, yeah, that's okay. I
Okay,
can.
so it's okay.
Sure. Yeah.
Okay.
Okay, I think we can start now.
Okay. We start now.
Yep. This is
okay. Welcome everyone for this physics colloquium, and we are very happy to have Dr. Alvin Chua to come and give a very interesting talk on space-based observing, the final frontier of gravitational wave astronomy. Now, Alvin is currently a postdoctoral researcher at Caltech and a member of the LIGO scientific collaboration and the LISA consortium. I'll leave him to explain what LIGO and LISA mean later. His current research interests are in gravitational physics, i.e. gravitational waves, black holes, general relativity, which many young people are very interested in, and data science as well, Bayesian statistics, data analysis, machine learning, with a strong focus on areas where the two fields overlap. He's also a born and bred Singaporean. I'll leave him to say a little bit about his history and how he ended up in Caltech.
Okay.
Alvin, over to you.
Thanks for the introduction, Albert. So, well, I guess it's quite a long story, so maybe I'll just keep it short by saying what I actually, when I was introducing myself to David at the start of the call. I'm actually a Singaporean, as Albert says. I'm a second career scientist, so I actually did sort of my first round of tertiary education in Singapore. I was a journalist actually, so I've worked at the newspaper at the Straits Times as an editor for a few years, and then I decided I needed a career change. So then I basically had to start from scratch. I went to Australia for another undergrad, and then I did my PhD at Cambridge before moving on to do my postdoc, my first postdoc at the NASA Jet Propulsion Laboratory, which is just down the road from Caltech. And just last year, I moved to Caltech. So, yeah. So in terms of like academic age, I'm still quite young, but in terms of physical age, I would say I'm not. So hopefully that introduction was not too boring. But okay, so I'll start my talk. Again, thanks to Albert, to Prof. Chia for the opportunity to give this virtual seminar. So my talk today will be on the topic of gravitational wave astronomy, with a particular focus on near future observing that we can do with space-based detectors such as LISA. So there's an illustration of the LISA satellites in the top corner here of this slide. So as you might be aware, gravitational wave science has become a very active subfield of astronomy since the LIGO discovery of gravitational waves from a binary black hole merger back in 2015. But as the field matures, there is a growing need to do the science analysis better, be it more accurately or more efficiently, or both. And there are also many open problems that must be solved if we are to achieve the scientific goals of LISA as well as other future detectors. So one of my main aims with this talk is to try and convey why it's important to develop modern techniques, computational and statistical techniques, in order to solve complex problems in gravitational wave astronomy. So before I begin, I should also point out that I gave a related seminar to the math division just 2 months ago, actually. So some of what I'm going to say here, in particular, the background sections may feel a bit like deja vu if you attended that talk. So I apologize. Okay, so in the first part of my talk, I'll give a very broad introduction to this new field. So I'll start by describing what gravitational waves are, what generates them, and how they interact with matter. Now, then talk about the inverse problem in gravitational wave astronomy. So this is the problem of how to link theory and observation so as to draw astronomical conclusions from detector data. Then I'll also briefly recap the main results from the past 5 years of ground-based observing, which is conducted using interferometric detectors such as LIGO, as well as pulsar-timing arrays with radio telescopes. And because this topic is probably quite new to most in the audience, the second part of my talk will still be quite heavy on the background. So here I'll then introduce the space-based detector LISA. So this is one of my main research interests. And I'll focus on a particularly complex class of LISA source known as extreme mass ratio inspirals, or EMRIs for short. And then in the third part of my talk, I'll then go into some of the modern techniques that I've contributed to the field, with the general aim being to solve the above inverse problems in a better way, or to even solve them at all sometimes. Okay, so what are gravitational waves? They are radiative perturbations in the gravitational field, and they are a generic consequence of any theory of gravitation with a finite speed of propagation. So in general relativity, gravity is simply the curvature of space-time, and its evolution is governed by the famous Einstein field equations, which are written here. So these equations essentially tell us that objects with mass curve space-time, and simultaneously space-time tells the objects how to move. So gravitational waves are generated by accelerating masses, or more precisely by systems with accelerating mass quadrupole moments. So what this means is that most moving objects will actually produce them, and it's easier to ask what doesn't. So a particle that moves in a straight line at constant speed will not produce gravitational waves. A perfectly symmetric spinning disk or sphere will not produce them. And also a pulsating sphere that expands or contracts radially will not produce them as well. So although there are gravitational waves all around us, they interact very weakly with matter. And therefore, radiation from everyday moving objects is far too weak to be detected, because such objects are simply not massive enough. So astrophysical objects are massive enough, but most of them are still moving too slowly in order to generate strong radiation. So as an example, Jupiter going around the sun only emits about 5 kilowatts of gravitational waves. That's roughly the power output of a large electric heater. Therefore, the generation of gravitational waves that we can detect will require extremely energetic astrophysical objects. So these include neutron stars, black holes, and other very compact objects, or core collapse supernovae, or the rapid expansion of the early universe itself. Okay, so far away from their source, gravitational waves have a simple description with a particular choice of coordinate system. So they are essentially spatial plane waves. You can think of them as spatial plane waves with two polarization states, known as the plus and the cross modes. So as such a wave passes through the plane of the screen, the plus mode will cause a ring of points arranged on the screen to oscillate as above, while the cross mode has the same effect, just rotated by 45 degrees. So we can consider the effect of a plus polarized wave on three inertial test masses, which we can set up in an interferometer-like configuration. So in the standard description, the masses have fixed coordinates. It's actually the metric of space-time, that is the way in which we measure distances. It's that metric that changes differently in the two directions. It oscillates, basically. So therefore, light travel time in these two directions also changes differently. And this is a measurable physical effect. But a common misconception is that it's not necessary to use light to measure this effect, nor is it necessary to have inertial masses. So for example, the masses can be electromagnetically bound particles in a rigid object. So it's easier to see why this is the case if we shift to a lab frame where the metric is now constant and it's the masses that move instead. So this gives rise to an effective gravitational force that acts on the masses. And in this description, if the masses are inertial, then the distance between them would explicitly change, while if they are bound, then they would be subject to stresses and strains. So gravitational waves then have very real physical effects. They can transfer energy and angular momentum away from sources, and they also interact with matter in a very tangible way. However, these effects are all very tiny, even for the most energetic astrophysical sources. And that's simply because they are so far away. So by the time their signals reach our solar system, they typically cause a strain or a relative change in length that is smaller than 10 to the minus 15. Okay, so now I'll abstractify the problem a bit more. So as mentioned earlier, an inverse problem is about drawing conclusions from data. And so it's naturally located at the interface between gravitational wave theory and also the observation methods that we use. So on the theory side, for gravitational wave astronomy, most of the sources that we can detect and study are astrophysical objects, such as black holes, neutron stars, and white dwarfs. And these sources can be isolated individuals, but more typically they occur as binaries and as populations of such binaries. And more speculatively, gravitational waves can be generated by various exotic cosmological objects that might be produced by early universe processes such as inflation and phase transitions. Gravitational waves can also be used to study gravitation itself by performing precision tests of general relativity or alternative theories in the strongly gravitating regime. And in the future, as the precision of observations increases, it might even be possible to study quantum gravity with these waves, for example, by constraining the mass of the graviton or by searching for quantum effects near the horizons of black holes. Okay, so that's the theory side. On the observation side, many methods of detecting gravitational waves have been conceived. So some of these are more developed than others. But all of these can be put into basically four main categories. So we can use resonant oscillations in bound objects, such as metal bars, superfluid helium, possibly even the Earth or the Sun itself, in order to try and detect these waves. We can also have man-made detectors that use laser or atom interferometry. So the former of which, of course, is the technique that's used in LIGO and VISA. And then we can even use astrophysical objects as giant interferometers with the Earth basically at the base. So this is done by searching for the effects of gravitational waves in pulsar timing data from radio telescopes or in astrometric observations from star surveys. And finally, we can use sort of indirect detection methods, for example, by observing the orbital decay of binary pulsars, such as the famous House-Taylor system, or by searching for distinctive polarization patterns in cosmic microwave background data. So that was a very broad sort of picture. So if we talk about the inverse problem in gravitational wave astronomy, it's fundamentally a bit different from other inverse problems in traditional astronomy. So that's because very detailed models of sources are often needed in order to detect their signals in the first place. So this is mainly the case for cleaner systems, such as binaries, where the gravitational waveforms can, in principle, be modeled to a very good degree of accuracy. However, most of these waveform models must be constructed using the physics of strong gravity, and that's both very theoretically and computationally challenging. Now, for less cleanly modeled sources, such as supernovae or stochastic backgrounds of signals, it's usually sufficient to describe these by computing, approximate power spectra of their radiation. And finally, with the growing catalog of gravitational sources, which I'll talk about later, models of source populations are also starting to come into play in terms of source modeling. So these allow observations to directly constrain astronomical laws in addition to individual source properties. Okay, so these waveform models that I was talking about, they are particularly crucial for gravitational wave astronomy due to the fact that time series data from the detectors is actually dominated by noise. And so the instantaneous signal to noise ratio, the ratio between the power, is very low, except for the loudest sources. Therefore, the data stream must often be filtered against waveforms in order to accumulate this SNR and extract any signals that they are buried in the data. So there are two main procedures in data analysis. So the first is detection of signals. So signals are searched for across the model parameter space, and then statistical significance is assigned to any candidates that are identified. Now, the second is parameter estimation. So here, the framework of Bayesian inference is adopted, and that's just because astronomical observations, you can't repeat them like an experiment in the usual frequentist way. So in this Bayesian framework, we estimate the posterior probability for the model parameters given the data and astrophysical priors. So this is done in practice by exploring and mapping out the posterior probability surface over parameter space for any source that we know is in the data. So both of these procedures, detection and parameter estimation, can be very computationally expensive in practice because data must typically be compared against a very large number of possible waveforms. Okay, so for the rest of this talk, I will focus only on my area of interest and expertise. So this area is source modeling for black hole binaries, and binaries are the most important type of gravitational wave source, and also data analysis specifically for laser interferometers such as LIGO and LISA. Okay, but before I go on to talk about space-based observing with LISA, so I'll give a very brief update on the present status of ground-based observing with interferometric detectors and pulsar-timing arrays. So there's a current network of 4 ground-based interferometers observing in the sub-kilohertz frequency range. And this network comprises the 2 LIGO detectors in the US, Virgo in Italy, and Kagura in Japan. So together, they have detected exactly 50 stellar mass binary mergers to date. So the first observing run of this network was undertaken by just 2 LIGO detectors. So it resulted in the well-publicized discovery of this binary black hole merger, GW150914, as well as 2 other sources. So 150914 was essentially 2 discoveries for the price of 1. It's not just the first direct detection of gravitational waves, it's also the first direct observation of 2 merging black holes. So these plots here, of course, will be very familiar if you're following the news in 2016. So they show the actual noisy signal that appeared nearly simultaneously in the 2 LIGO detectors, which are located at both ends of the continental United States. Okay, so a few more black hole mergers were detected in the second observing run. And towards the end of the run, LIGO was joined by Virgo. And together they saw the first neutron star binary merger, GW170817. So this was also the first gravitational wave observation with an electromagnetic counterpart. And indeed, it had several such counterparts because the merger was seen across the EM spectrum from gamma rays all the way to radio waves. So for example, the gamma ray burst, which was shown in the top plot here, was picked up by Fermi just 1.7 seconds after the time of merger, which was estimated, you can see from the frequency track of the source in the spectrogram of LIGO data in the bottom panel. Okay, so the third observing run was divided into 2 halves, but the second was cut short by the pandemic just after Kagura, the Japanese detector, started taking data. And nevertheless, this run contributed nearly 40 of the 50 sources so far. And one notable source was the black hole binary merger GW190521. So this produced the first known black hole in the intermediate mass range of between 100 and 1,000 solar masses. So there was also GW190814. So this was a binary merger with the smaller mass falling in the so-called mass gap between neutron stars and black holes, so that it's not clear whether it was a heavy neutron star or a light black hole. So these are examples of some of the more interesting sources that were found. And all 50 stellar mass mergers from the 3 runs are essentially depicted in this plot here by the vertical curves that join the 2 lighter masses to a heavier one, the larger black hole. Okay, so all of those sources were at the high frequency end of the gravitational wave spectrum. So at the other end, pulsar-timing arrays can be used to detect gravitational waves with nanohertz frequencies. So there are 3 such projects that are currently ongoing. They've been taking data for over 10 years. So these are Parcel in Australia, EPTA in Europe, and Nanograph in the US. So the idea behind pulsar-timing arrays is that millisecond pulsars are very stable astronomical clocks. And so the pulse time of arrivals can be predicted to very high accuracy. So if you have a stochastic background of gravitational waves from the cosmological population of supermassive black hole binaries, this background would then perturb the pulse time of arrivals by tens of nanoseconds each way. And it would do so, the key is that it would do so differently for each pulsar depending on where it is on the sky. So the key signature of such a background would be if we saw quadrupolar spatial correlations in the timing residuals. And these would not be present if the background does not exist. So very recently, a paper was put out by the Nanograph collaboration analyzing 12.5 years of pulsar timing data. So in it, they reported significant statistical evidence for the presence of a stochastic process that is common, that was seen by all the pulsars in the array. And they used several models to measure the amplitude, common amplitude, and spectral slope of this process. And all of these were consistent with the prediction for the power law spectrum for this population of supermassive black hole binaries. And the predicted value for that spectral slope is indicated by the vertical line in this plot here. However, they were unable to recover this quadrupolar spatial correlations that I talked about with sufficient evidence. And so they can't really claim a detection of the stochastic background. So a follow-up analysis of a longer 15-year data set might finally lead to such a detection, but we'll have to wait and see. Okay, now let's move on to space-based observing. So this is in many ways the final frontier of gravitational wave astronomy. And it's also the area that personally excites me the most because it has the greatest scientific potential, and it also contains many difficult open problems. So here I'll introduce LISA, which is the representative example of a space-based gravitational wave detector. And I'll discuss the key unresolved issues relating to the inverse problem for LISA. I'll also specifically focus on the inverse problem for extreme mass ratio inspirals. So these MREs are an important class of source for LISA, and their inverse problem is arguably the most challenging in the entire field. Okay, so LISA stands for the Laser Interferometer Space Antenna. So its design essentially features 6 inertial masses, test masses, which are housed in 3 spacecraft, so two to a spacecraft. Spacecraft are separated by 2.5 million kilometers, and they communicate with one another through laser transponders, and they are also drag-free in the sense that they don't apply forces to the masses along the interferometry axis. So they just follow the masses along their orbit. So LISA will be placed in orbit around the sun, trailing 20 degrees behind the Earth, and this animation shows the cartwheeling motion of the constellation, the LISA constellation on its orbit. And the mission will be operational for 4 years with the possibility of extension up to 10. So LISA is in space because we want to observe the millihertz band of the gravitational wave sky. So this ranges from 0.1 millihertz to about 1 hertz. And the number and the variety of sources in this frequency band is far greater than in the kilohertz or nanohertz bands. And so there's a lot more astrophysics that we can do in this range. Now, putting a detector in space allows us to remove noise from large-scale changes in Earth's gravitational field, and it also allows longer arms, which give greater sensitivity at low frequencies. So the lengths of these arms are not constant, but the data essentially can be post-processed to give 3 sort of standard interferometric combinations, which are linearly independent. So 2 of these are essentially the familiar Michelson type interferometers, but with 60 instead of 90-degree arms. So these can be used to measure the 2 gravitational wave polarizations. Now the third combination is essentially a Sagnac interferometer. So this is a common path configuration, and it's largely insensitive to gravitational waves. It can be used to measure the noise in the data instead. So funding has been approved for LISA. It was selected as the 3rd large class mission in the European Space Agency's Cosmic Vision program, and the scheduled launch date is 2034. So that sounds far away, but work has already formally begun for some time now, and a prototype design for the instrument and the data processing framework is required by 2025. So this is when the mission will be formally adopted for the implementation phase. Okay, so here I'll briefly mention as well the proof of technology mission, LISA Pathfinder. So this concluded in 2017. It was a resounding success. So the Pathfinder mission had 2 inertial masses in the same spacecraft, just 40 centimeters apart. So the spacecraft was then placed in orbit around the Lagrange point between the Sun and the Earth. And because of the much shorter separation between these masses, Pathfinder was not sensitive to gravitational waves, naturally. But the aim of the mission is to successfully demonstrate the drag-free technology that will be required for LISA. So this was done by measuring the displacement between the 2 masses to within 0.01 nanometers. And this same precision will be achievable for LISA because it does not depend on the separation between the masses. So impressively, the performance of Pathfinder exceeded its own target, and it has already met the mission requirements of LISA itself. So in this plot here, the red line is the LISA noise requirement, and the blue curve below it is actual Pathfinder noise. Okay, so the science case for LISA is fantastic because LISA will observe a large population of sources at unprecedented precision. But there's a price to pay before we can access this scientific potential. Excuse me. So in addition to the obvious technological difficulties that are involved with such a large-scale space mission, there are also several unresolved issues in the LISA inverse problem that make it more complex than the same problem for ground-based observing. So the first of these is confusion. So this is the fact that LISA data will contain a large number of signals that overlap in both time and frequency. So in particular, there will be anywhere from 10 to 1,000 supermassive black hole binary mergers. These occur when two galaxies coalesce. There will also be 1 to 10,000 inspirals of stellar mass objects into the massive black holes. So these are the extreme mass ratio inspirals that I talked about. Now, most of all, there will be 10,000 to 100,000 white dwarf binaries in our own galaxy that will be resolvable in the data. So a small selection of all of these is shown in this plot of gravitational wave strain spectra here. So we can't just look for these signals, find them once, subtract them, and then move on to the next signal. So the reason is that doing so might strongly bias the significance of any other detections and the accuracy of their estimated parameters. So we require a global solution to this inverse problem, where all the signals are searched for and analyzed simultaneously. But it's not actually practical to do this fully simultaneously. So the possible compromise would be to handle the different source types separately, because they are relatively uncorrelated with one another. So this global fit algorithm will then involve separate code pipelines that both update and look up the existing solution for the LISA catalog repeatedly. And then the construction of this in turn makes the streamlining of techniques and codes very important, so that the global solution is not held up too much by having to wait for a single pipeline. Okay, so the second issue is searching for and resolving all these overlapping sources in the data. So for certain types of source, the size of the parameter space can be huge. So I don't just mean in terms of dimensionality. That's roughly the same as it is for ground-based sources, but also in terms of the information volume of the space. So as a result, credible regions for certain signals can be very localized and therefore very difficult to find in the full space. Now, the probability surface over this space can also be highly multimodal, especially for those source types where there are multiple signals, and so self-confusion is an issue. So this is mainly problematic for the galactic white dwarf binaries, which will overlap with each other a lot in parameter space, as shown in the plot here. Now, in terms of multimodality, we might also run into the problem of degeneracy, where even if you just have a single signal, it could cause multiple modes in the probability surface. Okay, so there are several search approaches that are used in ground-based observing, such as pre-computing a large bank of waveform templates to compare against the data. But because the parameter space is larger for LISA sources, this approach quickly becomes impractical. So therefore, stochastic algorithms will have to be employed for global exploration of the parameter space instead. So these search methods will likely be hierarchical with different resolutions, and they may require multiple passes over the data because they're stochastic. So you want reliable results, you have to run them again. However, the real difficulty is that even though this stochastic search is the most efficient way of covering parameter space, we will still require many waveform templates in these algorithms. And furthermore, generating these templates and performing operations on them can be very computationally expensive. But finally, the third issue is accuracy. So this is only really relevant for strong field sources with very high signal-to-noise ratios. So there you have a combination of complexity and strength, which leads to a very high degree of signal variability over parameter space. So the waveforms are very sensitive to small changes in parameters. So these sources are naturally the most interesting ones to study, but unfortunately, they are also the most difficult to model. And that's only referring to the modeling of the gravitational wave signal from the source, but the response of the LISA instrument to the signal is also non-trivial to model, because that depends on the orbits, the dynamical orbits of not just the 6 inertial masses, but also the 3 spacecraft that house them. So for many sources, we will end up in the regime where this theoretical error from imperfect modeling actually might exceed the statistical error that we expect due to noise. So this can lead to systematic bias. And in terms of how this translates into waveform errors, generally we'll need correlation errors, or what we call mismatches, of at most 10 to the minus 4 or so, in order to avoid bias. So as you can see in this histogram of typical errors for various current models, such accuracy is generally not achievable by existing techniques for ground-based observing. So achieving the required accuracy in our best models is already difficult in its own, but it's only the first step, because these models are then unlikely to be fast enough to be directly usable in data analysis. So we then have to use the accurate models as a base for informing and constructing more efficient ones. But at the same time, we have to ensure that these efficient models are still accurate enough to perform inference, because that's the whole point of having an accuracy requirement in the first place. And again, here the problem for LISA is that standard existing techniques that are used to build efficient models may not scale up to the full parameter space of some LISA sources. Okay, so let's put the spotlight on extreme mass ratio inspirals as promised, or MREs for short. So these are the late inspirals, the late orbits of binaries with a mass ratio that's smaller than 10 to the minus 4 or so. And they arise from the capture of stellar mass compact objects by massive black holes and galactic nuclei. So those MREs that emit in the LISA frequency band will have about 10,000 to 100,000 observable orbits, which occur deep in the strong gravitational field of the central black hole. And their signals will typically persist over the entire mission lifetime, which is at least 4 years, or a significant fraction of it. And at the same time, because of the strong field nature of these orbits, they can exhibit extreme versions of relativistic precession, and they can also retain significant eccentricity right up to the point where the small object plunges into the black hole. So this gives the signals a lot of harmonic complexity as well, as you can see in this illustration here. So the numerical methods that we use to model comparable mass binaries cannot be applied directly to MREs because of the greatly differing scales of length, mass, and time in the system. So the best approach here is to use black hole perturbation theory with the small mass ratio as the perturbation parameter. So we expand about small mass ratio. And the gravitational field of this compact object essentially causes a perturbation to the gravitational field of the large black hole, which can be expressed as an effective self-force on a test particle orbit in a rotating black hole spacetime. So in order to meet the LISA science requirements, we'll need MRE waveforms that remain fully in phase over the duration of the signal. So this will require us to compute this self-force up to the second order term. So a practical scheme for doing this was recently implemented. It's only for circular orbits in non-rotating space-time so far, but it still represents a significant breakthrough after more than a decade of work in this area. Okay, so unfortunately, in terms of the broader astrophysical environments in which MREs might form, many unknowns still remain. So as a result of all these unknowns, the expected number of MREs that would be observed by LISA actually spans 4 orders of magnitude, from possibly 1 or 0, if you're pessimistic, to tens of thousands. And another possibly important issue is the recently identified problem of brown dwarfs around massive black holes. So these are very small stars that are abundant in galaxies, and they can orbit very close to the central black hole for millions of years without being disrupted by the field of the black hole. So if brown dwarfs are generically present around other massive black holes, then they won't be directly observable by LISA, but they might perturb the orbits of regular MREs that we are interested in, and they might even reduce the likelihood of them forming due to scattering. So this presence of brown dwarfs might mess up modeling, analysis, and event rates, and there may be other unforeseen environmental effects to complicate matters as well. So then you might ask the question, why are we bothering with MREs? Is it really worth it? So I think there are several good reasons why it's worth it. So observations of MREs will complement traditional astronomy in probing evolution scenarios for massive black holes in galactic nuclei. And they could also be used as standard sirens to investigate the expansion history of the universe. And furthermore, measurements with MRE signals can be done to very high precision, and thus they have great potential for tests of fundamental physics. And another reason has to do with the global fit issue that I mentioned earlier. So even if LISA data contains just a single MRE signal, it has to be modeled accurately and then subtracted from the data in order not to bias the analysis of other sources. And the final reason, I guess, is more personal, is simply for the challenge. So pretty much everything about the Emery inverse problem is very challenging. So I'll briefly explain why this is the case. So recall from earlier, there are three main unresolved issues in the LISA inverse problem. So signal confusion, search algorithms, and high accuracy modeling. So we can look at this Emery problem in context by comparing it with the two other important types of source that LISA will observe. So galactic binaries and massive black hole mergers. So self-confusion is the main problem for galactic binaries. So models for the Milky Way essentially predict that there will be millions of these binaries emitting in the LISA band. Most of these will be unresolvable. They will form a background of confusion noise. So the remaining resolvable ones can still have significant overlap in frequency, and hence they must all be searched for and analyzed simultaneously. So there are many of them to resolve, but the search is actually helped by the simplicity of the waveform templates, because these are nearly monochromatic weak field sources, and therefore they are very easy to model. So conversely, for massive black hole mergers, the main difficulty is in modeling the complex waveforms with numerical relativity. And as a result, the search for these signals will involve more expensive templates, as well as credible regions that are fairly localized in parameter space. But search is helped because these signals are very loud, and also there are much fewer of them to find in the first place. So that means that self-confusion is essentially not going to be a problem for these sources at all, although they will affect other source signals simply due to the fact that they are so loud. So Emerys present, of course, the greatest challenge because they suffer from all three issues in the inverse problem. So search would be a problem due to expensive templates, very localized credible regions, and also a possibly large number of signals to resolve. Modeling is also difficult because it requires a high degree of accuracy, and it depends on expensive self-force calculations that we don't even have at the moment. And as for confusion, we don't actually know yet whether it will or won't be a problem. And this is largely because the event rates for Emerys are so uncertain, as I mentioned earlier. So I've just given some background on space-based observing and the sort of open problems it contains. So in this final part of my talk, I'll give a brief overview of my recent research activity in the area of gravitational-wave astronomy. So my main interests are to adapt or to devise computational and statistical techniques for solving complex problems in the field. In particular, some of the issues that I just mentioned for LISA and for Emerys. So I'll start off with the work that is more generally applicable to both ground and space-based observing, such as machine learning methods and also more general techniques in applied statistics. And then I'll introduce some Emery-specific developments that I'm involved with. So I'm currently chairing two Emery-related work packages for the International LISA Consortium. So most of my efforts here are actually in direct contribution to formal preparations for the LISA mission. And these preparations will take place over the next 10 years or so. And in fact, some of the more urgent tasks must be completed within the next 4 or 5 years. Okay, but just before I begin talking about that, let me briefly recap the takeaway from the second part of my talk. So there are three main unresolved issues in the LISA inverse problem. So signal confusion, search algorithms, and high accuracy modeling. So all of them are relevant for Emerys, which makes them the most challenging class of source to deal with. However, if you've been paying attention, you'll notice that the two themes of accuracy and efficiency keep cropping up over and over again. So you can then use a more reductionist way of viewing these issues. You can just simply say that our waveform models and our data analysis algorithms are either not accurate enough or not efficient enough, or sometimes both. So the difficulty, of course, is that there will always be a trade-off between accuracy and efficiency. So this is depicted in a sort of schematic way by the curve on this diagram, which represents the best possible set of tools that might be available to us for some particular task. So the cross on this diagram then represents the minimum accuracy and efficiency that's required to realistically perform this scientific task. So when applying a new technique to any task in gravitational-wave astronomy, the general goal is then to try and improve the trade-off. So either by doing things more accurately at the same efficiency, or by doing things more efficiently at the same accuracy. So both of these, of course, have the same effect, which is to expand the area under the curve. So there's also a possibility of doing things more cleverly, by which I mean to use the tools in a different way so that they can achieve the original task, but with reduced requirements. And the effect of this is then to shift the cross down towards the curve. So it's fair to say efficiency is usually not a hard requirement when you're doing science. But for LISA and for MRIs, the curve and the cross are actually so far removed that such work actually becomes necessary in order to achieve the basic aims of the mission. So in short, I would say this is the one side that broadly summarizes most of my research in gravitational-wave astronomy. Okay, so the first example, I'll talk about the use of artificial neural networks for various applications in gravitational-wave astronomy. So neural networks have been around for a while, but their usage in this field has only started growing rapidly in the last 3 years. So I was lucky enough to get into it quite early. And in scientific applications, we can think of neural networks as essentially nonlinear statistical models that can be used to perform classification and regression, but to do so in a highly efficient way. So neural networks typically comprise multiple layers of computational nodes called neurons, artificial neurons, between the input to the network and its output. So networks are very versatile models. They've been used for a large variety of applications in gravitational-wave astronomy, but there are 3 main classes of applications which are most relevant to the inverse problem in particular. And the first of these is waveform modeling. So together with my collaborators at JPL, we were the first to combine neural networks with a dimensional reduction technique called reduced order modeling in order to construct a fast parametrized fit for certain waveform quantities. So this work was published in PRL, and our technique is called Roman or reduced order modeling with artificial neurons. So this scatter plot here on the right shows the accuracy of our fit to a simple binary black hole model. So the yellow points across the parameter space of the model stand for test examples that were fitted with good accuracy, and the black points are poorly fitted ones. So in the domain of validity for our fit, which we define by the red line, the median accuracy is above 99.5%. So this method was later applied to construct fast stellar mass binary models for ground-based observing by other people, and also to MRI modeling by myself and a different group of collaborators. Okay, so another application is detection, where a network is trained to detect the presence of a gravitational wave signal in noisy data. So I won't talk about this too much because I personally haven't done any work in this area. But there's been a lot of follow-up research in this particular area, maybe because it's simpler. Okay, so the last application is parameter estimation. So our group at JPL, along with another group at Glasgow University, we use different methods to train a neural network such that it can estimate the true Bayesian posterior distribution for the source parameters given some noisy data. So we wrote another PRL on this method. Okay, so this plot here shows an example of 2-dimensional posterior estimates from our method for 5 different signals. So the red points that you see are the true signal locations in the mass parameters, while the black lines around them are the true posterior contours. So these are the contours of the distribution that you get if you really compute the posterior in the slow way. The yellow regions are the posteriors estimated by our neural network, and you can already see by eye that these are a good match to the true posteriors. And the most promising thing about such methods is that they can produce the posterior estimates almost instantaneously, whereas standard posterior sampling in gravitational wave analysis is usually a procedure that takes hours to even days. And shortly after our work, our two methods by our two groups were adapted and combined by a third group to train these improved networks that can handle higher dimensional posteriors with multimodal structure. Okay, so another machine learning technique that's widely used for fitting tasks in scientific applications is known as Gaussian process regression, also commonly known as kriging. So here, the numerical data to be fitted is modeled by a stochastic Gaussian process. So this is fully described by a covariance function, which is essentially trained on the data. So a nice byproduct of this method of Gaussian process regression is that it provides an easy way to quantify the Gaussian errors in the fit. So the most obvious applications are then in waveform modeling. So one example is a model for eccentric stellar mass binaries, which I helped to develop. And this model is now used routinely in ground-based observing. However, as an alternative to fitting numerical data during the modeling stage, we can also consider doing it on the data analysis end. And that's because any errors that you get in the waveforms, they're going to be effectively smeared out when you do analysis anyway. So the end product of the analysis is going to be a posterior distribution. Right, so the larger idea here is to marginalize over the error in the model. And the first step is to fit a Gaussian process to the error in a fast waveform model relative to a slower but more accurate model. So we can then use the fast model in the analysis together with a Bayesian likelihood function that has the Gaussian model error integrated out analytically beforehand. So the effect of this can be seen in this plot. So for a three-dimensional example where we're trying to measure the two masses of an emery and the spin of the larger mass. So the small cross in the center of each panel indicates the true signal location, while the red contours are for the posteriors that we would get if we use the fast model without accounting for model error. So these are clearly inconsistent with the right answer, but if we use the modified likelihood instead, then the posterior estimates in blue have corrected for this bias. So my collaborators and I first proposed this in the context of stellar mass binaries for ground-based observing, but we have since applied it to emeries as well. Okay, I'm going to skip this slide. I'm running a bit short of time. So in terms of emery-specific research, my earlier work essentially introduced a semi-relativistic waveform model, which is accurate and efficient enough to be used in data analysis. So we call this model the Augmented Analytic Klutch, or AAK, because it actually augments an older analytic model with the correct relativistic frequencies for generic orbits in the rotating spacetime. So as a result, the waveform phasing that we get from this AAK model is also accurate in a relativistic sense, but only up to an approximation to leading order in mass ratio. And recall I said earlier, for the purposes of laser science, we actually need this phasing, the exact phasing up to one order beyond the leading order. And also the waveform amplitudes from this model are also just calculated in the Newtonian approximation for simplicity. But regardless of all these approximations, the model is very useful for data analysis because its frequency content is much improved over the older analytic model. So you can see this from the comparison and plot here. So the red waveform is from the old model. The green waveform is from the augmented model, and the black waveform overlaid on both is from the some accurate reference model. So I've made this AAK model publicly available online, along with a couple of other first generation models, but I'm no longer developing and maintaining the software. And the reason is because it's now been superseded by another package, which I'll talk about shortly on the next slide. So the AAK model has seen usage in several data analysis studies so far, and those that I'm personally involved with are on the testing of relativity with emeries, as well as the marginalization of model error I described on the previous slide. And the model is also going to be used in the next round of LISA data challenges. So these are collaborative efforts by the LISA community to develop data analysis strategies on simulated data sets. Okay, so more recently, my collaborators and I have been developing a modular framework for the next generation of fully relativistic emery models. So this work was recently published in PRL. So the general idea here is to construct fast fits, not to the full waveform, but to the large set of harmonic amplitudes in an emery waveform. And we use methods such as the Roman neural networks that I described earlier. And the entire framework is also implemented natively for GPUs as well. So this is important if we are to meet the computational demands of the LISA science analysis. So the first model in this framework is only for the limited case of eccentric orbits in a non-rotating spacetime, but it is fully relativistic. And with the improved computational techniques in the framework, the time that's taken to generate such waveforms is actually reduced from hours down to milliseconds, as shown in this timing plot here. So in other words, we are now able to do data analysis directly with fully relativistic waveform models for the first time. And that's an important development in solving the Emery inverse problem for LISA. So our code is released online as part of the open source black hole perturbation toolkit. Now it also includes an improved version of the AAK model from the previous slide. So this model is still important for now because even though it's less accurate, data analysis studies, we typically need to use models that cover the full parameter space of generic Kerr orbits. And in addition, I've been working with a Japanese group on a new model that is generic and fully relativistic, but it's computed using a semi-analytic approximation. So this will be the next model that we will integrate within the framework. And finally, accurate numerical models that are generic and fully relativistic are currently under active development. And we have developed the underlying theory for this work in another recent paper. And the challenge now is actually to extend the fast fitting method to the larger parameter space of generic orbits. Okay, I really ran out of time, so I'm going to skip this last slide and just end with my summary. So to conclude, the age of gravitational-wave astronomy has begun with ground-based observing. And near future space-based observations of millihertz sources have even more scientific potential. But as I discussed in the second part of my talk, there are many difficult challenges in LISA source modeling and data analysis. And this prevents us essentially from unlocking that potential. But luckily, we still have time to resolve all of these open problems before LISA launches in the next decade. And finally, the various computational and statistical techniques that I introduced briefly in the final part of my talk will be useful for solving complex inverse problems, such as those for Emrys, which is a very active area of work, and it's also one of my main research interests. I think that's it from me. So thank you for your time.
Okay, thank you very much, Alvin, for the fascinating talk. I have to leave at 11. So after that, David will take over the Q&A session. Sorry about that. So okay. I just have a very, of course, I'm not in this field, so I'm just curious. You know your LISA thing, where you have the 3 satellites, right? As they move. The distance between any 2 of the 3 satellites throughout the motion, must they be very precisely determined?
Right. So yes, the answer is yes. So we have to determine the distances very precisely, but we can't control them very precisely. So I think
okay. How precise?
Oh, okay. Actually, I would say almost as precisely as you. That's a good question, actually. So okay. So they communicate through lasers, right? Yeah. So yeah, I would say we have to get the precision of their distances down to I would say the same precision that's achieved, and you can do that, I think, because you are using laser transponders, so you can laser ranging.
So it's down to what? Sorry, like millimeters or microns or nanometers or what?
I would say even nanometers.
Wow.
But again, it's really the photons that you worry about, right?
Yeah.
So as long as how do I put this? So you're more concerned with the relative sort of times of arrival. So as you send a photon off a single satellite to the other one, and then you actually get some delay because once it reaches the other satellite, it's sent back.
Yeah.
Yeah. So you can use that, and then if you send it along another arm, you get a slightly different answer, a slightly different time.
Okay.
And that's the important thing. You want the differences, so that allows you to measure.
And all those Doppler shifts must be taken into account, right?
Yeah, it's
obviously okay. Yeah. And the blue circle on your diagram is Earth, is it?
That is Earth, yeah. So it's
oh,
just
that's Earth. Okay. Okay.
But I think the reason we put it there is I think it is a stable point. It's not a Lagrange point, but I think it's stable, and also I think for convenience as well, right? Because it's sort of close to Earth.
Okay. Shao, you have a question?
Oh yeah. Hey, Alvin. Very nice talk. I have a question. So LIGO cover kilohertz detection band, and LISA cover subhertz. What about in between? Is there any plan for LIGO or LISA to construct any instrument that can detect in this tens of 100 hertz bands, or there's not much interest in
there is interest in it, because that band is also very astrophysically interesting. So I didn't mention these in my talk at all, but there are two ways you can go about doing it. So one is to stay on the ground. So these are essentially going to be like the third generation of ground-based detectors. So there's one in Europe called Cosmic Explorer is from the US, and then the Einstein Telescope is another initiative in Europe. So these they will essentially build the same sort of ground-based interferometers, but with longer arms and with better techniques, essentially. So that's one way you can get, with longer arms, you can go down to slightly lower frequencies, like in the decihertz range that you're talking about. So there've also been sort of proposals to do space-based detectors in that band as well. So again, it's going to be cheaper than LISA because you don't need such long arms. So there are again many different proposals, but as the current status is that none of them are funded. So some people would just say they are science fiction, but the ground-based ones, the third generation detectors, those are quite real. But again, they're not funded. But I would say they are more likely to happen.
I see. Okay, thank you.
Dan Qi, you raise your hand.
I have a question is in the chat.
Hi. Your question is in the chat.
Oh, okay.
Would I consider it a demanding field? I would say it's a very interesting field because it's very cross-disciplinary. So I would say it's a lot broader than most people actually think it is. So you can really come at it from the instrumental side, right? So there are plenty of people I know who work in like quantum optics and stuff, but they would consider themselves as well working in the field of gravitational astronomy. But I don't talk to them at all, right? I don't work with them, so it's quite far removed. So it really depends, I guess, what sort of particular sub area that you find really interesting. I would say I can speak for the area that I'm in, so which is the more theoretical side, and in fact closer towards the data science side. I would say I guess most fields are demanding, right? So, but I would say the techniques and knowledge that you need to use in this field, maybe you need to be a bit more general than most. So you need to know a bit more about everything. So in some sense, if you like being a generalist, then maybe this field would be quite interesting for you. Hope that answers your question.
Thank you, Dr. Chua.
No problem. So, Alvin, I have one last question before I leave. It's just, you can say it's asking for your advice. How can a small country like Singapore participate in projects like this, given our limited resources and lack of funding in this kind of very GR, astronomy type of research? How can we put our foot in?
That's a very relevant and question to me right now as well, because I'm trying to come back to Singapore, as you know. it's a good question. I don't think there is an answer because ultimately we are a small country, as you say. We have to choose what to prioritize, right? Everything is limited. Talent is limited. Manpower is limited. Funding is limited. So I think it's fair, you know, if we, you know, these funding agencies, we just decide that generally, you know, astronomy, astrophysics, or even like more theoretical physics, maybe it's less worthy of funding. Again, I don't know how how we could actually change that, but I guess, you know, but at the same time, there are Singaporean scientists who work in these areas, not just me. I know quite a few of them. So maybe an answer to your question would be to support these scientists, you know, so if you ever find yourself on a review panel reviewing one of these proposals, maybe that would be the way to go. I think we have to change our mindset as a community. I don't think there's any single thing anyone can do to change it, realistically speaking. You agree?
Okay, thank you. We'll talk more later offline. I'll get David to take over this session. Okay,
all right.
Bye.
Thanks for coming up. Bye.
Bye.
Thank you, Albert. So, any other questions? So actually, I have two questions for Alvia. So Alvian, so the first question is, you know, when you give the second observation of LIGO with Virgo, I think you say that there is also a direct, yes, this one, thank you. Yes, direct observation of light. And which I don't understand is that, so this is occurring quite some times after, right? So there is a delay. Can you remind me why this delay?
Why are you asking why there is a delay?
Yeah.
Okay, so well, essentially the system that was observed was two neutron stars, right? In a close binary, and essentially this track that you see is really the final seconds of it, as they really get close, and then so
Right.
this is called a chirp, right? Because it resembles the of a bird. So okay, so in terms of the electromagnetic signals, so those really come from, I would say, the surrounding environment as well, right? Not just the binary itself. So that's why there is a delay, like from the afterglow. So I would say gamma ray bursts are actually the closest in terms of time delay. So they happen right at the point, I would say almost right after you actually see the gravitational signal. Yeah,
right.
and you know,
are all traveling at speed of light, right?
They're all traveling at the speed of light. Yeah, that's true. But it's where the signal is coming from. So when you get like afterglow from the radio emission, so that comes later, and it is really from the stuff around it, I would say. Whereas with the gravitational wave signal, you are observing the actual objects themselves most directly. So it's a good question, right? Yeah, because yeah, and I think so with this close, because they occur so close to each other in time, you can actually use them to sort of constrain the speed of light, essentially. Oh, sorry, the speed of propagation of gravitational waves, because we know the speed of light, but it's not clear whether, you know, because in GR they do propagate at the speed of light, but they may not in other theories. So that's what you can use them for.
Okay, another question more related to your direct work. So on this very different mass ratio, I mean, I was surprised that somehow the prediction of such an event are so broad. I mean, so you say from basically 0, if you are pessimistic, to 10 to the 4. So I mean, we don't have a clearer idea of how many of this system are present.
Yeah, I think the problem with these sorts of binaries is that that the astrophysics is just unknown, because without gravitational waves, we can't even see them at all. Right? So in a sense, we don't know anything about them yet. So in some sense, we are relying on seeing them with gravitational waves in order to improve the astrophysics. So what astrophysics can tell us now is quite limited. I mean, you know, they've tried, but it's just not well understood. So there are a lot of uncertainties, like, you know, the fraction of massive black holes that are hosted in these dense stellar environments. So that's unknown. The intrinsic rate of at which these MREs form, also it's unknown. Yeah, so that's the reason for these very broad estimates. But I think, yeah, so, but generally, I would say we still have to prepare for them, right? So I always get this question, basically, if there's a possibility that there could be no MREs in the data, then is it really worthwhile, you know? Because some people actually spend their careers on these binaries. But I would say, yeah, for the reasons that I gave on this slide. So there are the positive reasons, you can get a lot of good science out of it, but there's also the negative reasons. You don't want to bias the other sources. You want to make sure the whole mission is a success.
Yeah, I think it makes sense to work on this. I have absolutely no problem on that. And in terms of energy dissipation, so how many energy dissipation in form of gravitational wave are you expecting from this object? So is it
energy?
Yeah, in terms of emission of gravitational wave, right? So the system will lose mass, will lose energy because it emits gravitational wave. I mean, you give this example between Jupiter and the Sun, and I remember the first observation that was very impressive. I mean, I think the system will lose something like more than a few solar masses in terms of gravitational wave. So in this kind of system, what are you expecting in terms of
Okay, that's a good question. I don't have the answer on hand because I'm not used to thinking of this in energy, because we generally look at the field itself, right? We look directly at it. But I would say it's similar to, I would say, the mass of the small object, because yeah, the amplitude of the signal scales with the mass of the small object. So naturally, I would say the emission, the power also goes with that squared, maybe.
I see. And this will lead to some kind of crash of the small object on the big object, or is mainly this energy is taken from the big object somehow, you know? So how it will perturb the trajectory, the orbits of the system?
So the big object is not really big because it's massive, but it's a black hole, so it's compact.
Right.
So what happens is yeah, so it will, so when the small object plunges, so by plunge I mean it essentially just goes from a stable orbit down into a non-stable one, and then it goes basically into the event horizon of the black hole. And then that would, yeah, so in the same way that, you know, when you have comparable mass mergers, they coalesce to form a single black hole. So right. This also happens, just that the big black hole is slightly perturbed. Yeah, I would say, yeah, there's very little change essentially to the big black hole because of the extreme mass ratio.
I see. Okay, thank you. Other question in the audience? Okay, so if not, thank you very much, Alvin. Hope to see you in Singapore soon.
Yeah, I hope so soon. Yeah, thank you for having me today.
Thank you.
Speaking to you all.
Yeah, thank you for the very nice talk. Have a nice evening.
Yeah.
Goodbye.
See you. Bye.
Bye.